My name is Kriti Srivastava, and my other teammates from industrial engineering are Roger Riviere, Wilson Lau, and Douglas Nguyen. And my project for the senior project class was based on Smart Factory, and it involves standardization in the SMT manufacturing line using SexGen protocol. So just to give you a brief overview of how the presentation is going to go, I will be briefly talking about the background, where I will be explaining what exactly Smart Factory is, and diving deep into it, I would just give you an illustration of how Smart Factory works, and then we will talk about the gap in the market, SMT, and what exactly Industry 4.0 smart manufacturing is, literature review of the standardization tool, SexGen, and my motivation as a biomedical engineering student to do this. The objective of the project, FDA considerations, design of experiments, methods, results, conclusions, and cost analysis, and of course the future work. So starting on with the concept of smart manufacturing. Smart manufacturing is actually defined as the age of industrial revolution where you have connected systems. So if you have 5 different machines, smart manufacturing enables you to connect all those machines together and get the data in a central cloud-based system, pretty much. So as you can see, the first industrial revolution was just based on mechanization, followed by the production of electricity, and then we had computer and automation, which was a huge industrial revolution, and now we have the 4th industrial revolution, where we are building up cyber physical systems, which connects different machines. So what exactly is surface mount technology? Surface mount technology, the method on which our project is based, is a method of producing printed electronic circuit boards. So, and the machine that we are particularly focusing on this project was Fuji NXT pick and place machine. So what it does is like it picks up the parts and places it onto the printed circuit board. So just to give you a brief overview of how the NXT pick and place machine works. That's the pick and place machine picking up the parts, placing it onto the boards. Now, what was my motivation and my team's motivation to do this project? When we were doing our market trend, we found out that the US Bureau of Labor Statistics has noted a decrease in the manufacturing productivity. So as you can see, 1987 to 2002, there was a huge boom in the production line, but then it's gradually started decreasing, right? And going further into this market trend analysis, we found out that there's a lack of standardization, which causes the production of a lot of defects in the PCBs, and that's why the SMT manufacturing line has been gradually going down. And so, to combat this problem in the market, we are trying to revolutionize the SMT manufacturing line using the concept of Industry 4.0, which as I explained before, is a concept where you connect different machines together through an automated system. And we found out that there is a protocol called SexGen that is exclusively used in the semiconductor world currently, not much in the manufacturing line. And what this protocol is capable of, that it can actually control your machines and help you receive data from all the manufacturing line in the same standard manufacturing format. So as I was saying, the purpose is actually to standardize, which SexGen really makes us achieve it. So what exactly is SexGen protocol? Going into the literature of it, it's actually a connectivity standard, and it was developed by a non-governmental organization called SEMI. They are based in Milpitas actually, and it actually enables two-way communication between different machines. It gives us excellent feature like helps us build automated systems. It is a measurement tool for how your machine is performing. It is capable of giving you alarm and event reports to see what's wrong and what's right in your machines. And of course, it helps you to enable traceability in your machine, so you can just track down all the different parts that went on to produce one single printed circuit board. And as this figure explains, SexGen is a broker kind of system where it actually takes the information from your equipment, which is the source, takes it to the client, which is the host, a central data repository where you can retrieve all your data. And there are several components, actually over 50 components to the entire SexGen protocol. To name a few, Sex1, also called Semi4, Sex2, Semi-E5, GEM, Semi-E30, and high-speed message services, HSMS service, Semi-E37. But we are not, of course, we are not interested in the wide-scale application of what all SexGen can do. We, in our project, due to the limited scope of our project, focused on Sex2, which is the standard that defines message content layer, basic rules of handshaking between different machines. So basically, this is the part of SexGen that enables two-way communication between the machine and the central data repository. And also, using this, we found out that we can actually achieve the compound annual growth rate of about 4.4% if things are standardized using SexGen protocol. So as you might by now feel that this is a project heavily based on electronics, right? And my motivation as a biomedical engineer, what is it exactly? So I found out through my research that a lot of medical devices, like your monitors, to name a few, blood glucose monitors, heart rate, blood pressure monitors, scanning technologies, internal devices like heart pacemakers, and scientific instruments like photometers, electronic microscopes, they actually use PCBs in their electronic circuit design. So if you can imagine, if something goes wrong in the PCBs, it can heavily lead to the failure of these important integral medical devices that all biomedical engineers produce. Also, to add on to this, I researched and found out that FDA actually has seen a rise in the manufacturing defect, because of which the devices have to be recalled, and it has been steeply increasing. So in 2003, as you can see, there were about 604 devices recalled. Moving on to the era of late 2000s, you see that over 1,000 medical devices are recalled every year, and this is about 44% of the manufacturing recalls that's been happening. So this really tells that we need to do something better in the manufacturing level. And continuing on with the motivation from the manufacturing perspective, if the PCB manufacturing process is standardized using SexGen protocol, it can really help us to build up manufacturing level statistical analysis. We can do work and we can track down the work in progress that's happening in our manufacturing productivity line. We can always calculate the overall equipment efficiency of our devices, because now we have real-time data coming in through the SexGen protocol. We can also look up for the process indicators that's coming from different devices in the SMT manufacturing world, and of course we can do quality management using statistical process control. And just to reiterate, the project objective is to record machine operation by using the data using the standard SexGen protocol. And FDA considerations, as I was earlier stating, that pacemakers, which is a class 3 device as you can see, actually uses printed circuit boards in its electronic circuit. And this really motivates me to do this project, because you can imagine if something goes wrong in the PCB that is embedded in this pacemaker, it can lead to the device failure and ultimately to the death of patient. So that's kind of really important. So looking at the design of experiment for this project, there are a lot of real-time data that comes from the SexGen protocol, but due to the limited scope of our project, particularly the calculations that we did using the data was for the nozzle usage. So nozzle is basically the tip of the head that picks up the part, and there were actually two levels of it, or basically two parameters that we were judging: the error count and the pickup actions of the nozzle. And second second parameter that we were judging in this entire experiment or the design of activity was the calculation of cycle time, which is very important from the manufacturing perspective, as it tells you how long did the device take to manufacture, let's say, one printed circuit board. So for the methods, it was a very straightforward methodology that we followed to achieve what we wanted to achieve, that is standardization. For this, the first step was to prepare our printed circuit boards, basically to tape them up like this. As you can see, there is a tape and the central line of this PCB. So we taped the printed circuit boards and the reason why we taped is because we wanted to induce errors. Usually you would apply solder, right, to place the part on the printed circuit boards, but when you place it on the tape, like there is a higher chance of inducing the errors. So we tape run the boards for the test runs that we were doing. Followed by this, these were put into the Fuji NXT pick and place machine that I was earlier explaining was the equipment that we used in this entire project. And as this block diagram explains, so here we have the Fuji NXT pick and place machine where we were placing the printed circuit boards. And there was a switch in networking language, it's called switch or it's called a hub, which actually configures the NXT pick and place machine to the Nexim host, which was another software that extruded sextrim compliant data from the Fuji NXT pick and place machine, extruded it through the switch or the hub. It was a T1000 24 port switch or hub, and once we had the data on the Nexim host, it again transferred it to another switch or the hub, which transferred the sextrim data to the central data repository that we called it in our project Cimetrix host. So it's produced by a company called Cimetrix, and what it does is like it acts as a data repository where you can automatically get the Excel files from the production runs and see what's happening through your machine real time. And in the future, this is a kind of data repository, but not exactly a data repository because it doesn't have a capability of storing large size data. So in the future, like we would connect the Cimetrix host to another future data repository, which would have maybe, let's say, the data for the entire production line that's happening. Moving on to the results, we were hoping, since sextrim is a very new concept, it's been around in the semiconductor world for around 20 years, but it's very new to the manufacturing world. So we were very interested to see how the sextrim data looks like, or particularly the sex2 data that's coming from the machine look like. And the first initial acquisition of data that we received in our central data repository, also called the Cimetrix host or Cimetrix HostConnect, was a screen, basically a central screen like this, from where you can go to the collected events and alarm reports and the custom messages coming out from the sextrim machine. The Fuji NXT pick and place machine, the sextrim compliant data coming out of it. And as you can see, as this highlighted part suggests, it was actually a string of data or a string of report IDs. So basically, when you click on to any of these report IDs, you would go on and get individual data, performance data, or the production data coming out of. And these report IDs actually mean something from the sextrim point of view, as one of them can mean nozzle usage, the other one can mean head usage, the other one can mean defective parts, and things like that. And just to illustrate, what happens after we collect in any one of these IDs is what you get is initially what we got was a string of numbers, or let's say alphanumeric string like these, which actually kind of didn't mean anything at the beginning because the challenge initially for the project was we didn't have the sextrim manual where we could go on and see what each of these strings or each of these alphanumeric characters in the string mean. So what we had to do is we had to talk to the Cimetrix people individually and ask them, can you please go to the sextrim manual and explain what these numbers mean, and then we got the legends. So this is an illustration of the nozzle usage data that we received while doing the experiment. So the first number, for example, means which nozzle station number were you using. The second number means what was the pit number you were using. The third, S31, actually means the nozzle ID, which is again a part of traceability. And station ID again is a part of traceability. Station name again a part of traceability. And then comes the production interesting data, which is the pickup actions. So as you can see, we had 102 pickup actions for one of our nozzles, which is a great huge number from the manufacturing perspective. Followed by the number of errors. For the first one, it was 0, which is great, but ideally it doesn't really happen that way. And then parts rejected by the machine. So parts rejected by the nozzle is one different thing. Parts rejected by machine is, did your machine stop during the production in between? And then parts not picked, again, did the nozzle missed picking up one part from during the production? And rescans and empty pickups. Those are the kind of data, SexGen compliant data, that we particularly collected for the nozzle usage, as you can see from this diagram. And so as I was explaining, we had to talk to the Cimetrix people continuously and actually ask them what each of these alphanumeric characters mean. In the long run, since this is just a beginning of this project, we would eventually have got the SexGen manual to refer the data to, but then it's kind of hard for an engineer to actually go back and forth and relate every number to something, to a legend from the manual, right? So we had to build up a system using C programming that would eventually store all the data automatically coming out of the Cimetrix host, and we saved all our production data into the form of CSV file or Excel files, as you can see. So whatever I was explaining earlier in this slide is actually now contextualized into a readable format. So you have the time, you have the line, you have the machine module, you have the module number, you have the station number, the pit number, the ID, nozzle station number, the pickup actions, errors, and so on and so forth, now contextualized for you in an Excel file, which now makes it easier for an engineer to go back and just analyze the data. So that was the second phase of our project. First, standardizing the machines using SexGen, using the block diagram configuration that I was explaining in the methodology, and then contextualizing the data into a readable format that can be read and analyzed. And some of the things that in the future, like this is not all that we can do because SexGen gives you a huge ton of data, huge data repository. But some of the things that you can do from a manufacturing point of view is you can make a Pareto chart like we did in our case for the error counts of the nozzle usage. So while comparing the 6 nozzles that we used in our production, we figured out, like, for example, S11-08555 had the highest error count. So if this kind of data repeats from S11-08555, it tells an engineer that there is something wrong with this particular nozzle, and the engineer might want to check what's going on, because this can actually lead to more defective production and ultimately cost a huge ton of money to a manufacturing industry like Jabil. And on the other hand, one of the positive things that you can evaluate is which nozzle was performing the best. And while evaluating different nozzles, we found out that T113-05630 nozzle ID with the nozzle ID this had the highest pickup actions. And if something is going right this way, you can again go back to the production data that you're receiving real time from the production using SexGen and see what's so good about that part and why are the other nozzle parts underperforming compared to this one. So there can be a lot of analysis going on this way. And of course, as I was saying, the second parameter that we were particularly interested in was the cycle time. So since we used Fuji NXT pick and place machine, there were 2 modules that we were using, NXT2 and NXT3. NXT2 in our case had a higher cycle time, as you can see, about 37 minutes, as you can see from the chart, while NXT3 had a lower cycle time. And if this kind of huge discrepancy exists in the manufacturing line, you can always, as an engineer, look up to it and see what's going on. Why is my, let's say, NXT2 underperforming? Why is it having such a higher cycle time? There's a standard cycle time that it should follow, and there can be a lot of analysis done to it. And this is again just an example of a snip actually of the gem controlled real-time data that we were receiving. So you can also actually track down, as I am saying, SexGem data is a real-time data. So you can see like you get data every minute. It just, as your production is running, the data is populating every minute, and it just tells you like if your machine paused for a moment, when did it pause, what time did it pause, what was the date on it, and like on the included reports, when you go to the included reports, you can see what was actually happening behind it. So that's why SexGem data is very much real time. So every minute it populates data and tells you what's going on with your production line. So to conclude, as our project objective was to connect, configure and collect the data coming out of the Fuji NXT pick and place machine, that was very much accomplished. And the happiest part of this project was the data was real time. So right now, industries like Jabil, the existing softwares, the existing configuration that they were following, didn't get them the data in a real time fashion. So when the existing software that they were using, it just gave them the summary of how exactly the overall production was, but it really didn't tell like what was going on every minute. And when something goes wrong in the long run, you need to go and track down the data for every minute and see what was wrong and what was right. So SexGem data really indeed helped us to connect, configure and collect data from different machines. And just the cost analysis of it, since we were using, it was more of a networking and electronics methodology based project. So there was not really any consumables in our project. We did pay for the communication hub or the switch that I was mentioning in the block diagram, and the number of we had people from Fuji coming in and Cimetrix coming in to help us to accomplish this project, and that's their cost, as you can see. And there is actually a lot of future work. What we were doing was basically laying down the groundwork for the Industry 4.0 concept, where we have to connect every different machines using an automated system. And future work will actually include creation of a database, dashboard for a real-time monitoring data system, and which can be used to see what's happening in your production line. So if you're an engineer who is not present in the manufacturing line, you can just go up and see, you can just look into your dashboard through an app and see what's going on in your production line every minute. So that would be the main future work that we would be doing. And of course, we would be applying high-level data analytics to see what's wrong, what's right, and why are things not functioning as they're supposed to, using the real-time data from the SexGem compliant machines. And these are the references. And I would really like to thank Dr. Guna Salvadori for actually giving me and students like me the opportunity to work with Jabil, Dr. Folarin Erogbogbo for continuously guiding us throughout this senior project class, my Jabil advisor, Dr. Barez, for again providing his critical feedback every minute, my Jabil advisor, Mark Tudman, for being so supportive and mentoring us in every stage of this project, Nguyen, director of Jabil, for his support, Rosa Javedi for her support, Jennifer Gamboa, who helped us do the test runs, and Sundar and Dan Kos from Cimetrix, John Versigan and Atul Handa, who helped us continuously to achieve what we were intending to achieve in this project. And that's all. Thank you so much.